colloquium, which is also part of the Yahoo database talk series. Today we are very happy to have with us Professor Shivnat Babu from Duke University. Shivnat has a PhD from Stanford University and a bunch of awards, including an NSF Career Award, several IBM faculty awards, and more. And he's known for a whole bunch of different kinds of work, including database autonomics, which is something we'll be talking about today.
Thanks, Magda. So this is joint work that I'm doing with a whole bunch of students, only some of whose names are listed here because the list was actually becoming very long, and these are the students whose work I'll be talking about. So this work, the name of the project is Starfish, and what I'm going to, you'll actually see two terms here which probably do not make that much sense, MADDER and self-tuning, and I'll actually describe both of them as we go along. So big data, any conference you go to, any place you go to, big data analytics is something you must, you probably can't escape. And often what you hear about are these very big companies, Google, Yahoo, Facebook, who have petabyte scale warehouses, right? And there's very big data. But there are a whole bunch of even smaller players in the big data world. And one very good example, I know that at Washington you're actually doing a whole bunch of work with scientists. One very sort of interesting experience and collaboration that we have at Duke is actually with the Center for Public Policy, and there is a Center for what is called computational journalism. And the Duke student newspaper also has a data-driven journalism section. So the theme there is the following. Newspapers, as you probably are, newspapers, especially the ones in print, are like losing money, losing funds. So what they are really cutting are on the investigative journalism. So the hope is we can replace, and journalism is very human-intensive, labor-intensive. So the hope there is to replace some of those parts with computing. And the best example I can give is, imagine WikiLeaks. So somebody actually makes a whole bunch of data available online, and then journalists are really scrambling to extract some good leads, which could lead to some good stories out of that data. Right? So these people don't have petabytes of, even terabytes of data. But what makes even them be interested in big data analytics is it's not just the raw size of data, right? It's also what are you doing with that data. And most of these people don't just want to do grouping and aggregation and these sort of things, which as database people we often end up doing or imagining that people do. But they want to do very sophisticated machine learning analysis, or they want to treat the data as matrices and do some linear algebra. So there are sophisticated analysis that people want to do. So Starfish was basically our, like 2 years back, that's when the project really started. So we were actually sitting and thinking, we want to build a system that can do big data analytics. So what sort of features should the system have? What are practitioners of big data analytics looking for in a system for big data analytics, of course? And Starfish was basically our answer, and it's basically a system that is that's still, I think there's a good 3-4 years of work more left in the system. But let me give you a very quick overview so that you have a context going forward. So Starfish is built for now on the Hadoop ecosystem. So this is basically, Hadoop is a popular open source implementation of the MapReduce framework, and the MapReduce framework has two aspects. There's a distributed file system. In Hadoop, it's a Hadoop distributed file system. In a Google's context, it's basically the Google file system. And there's a MapReduce execution engine, which takes care of scheduling and setting up all of these slaves and all of those things. And a very important thing, and this is what people often miss. When people say Hadoop, they're often referring to the entire Hadoop ecosystem. And that's much, much more richer than just the MapReduce execution engine and the file system. For example, people can write, at Yahoo, there are machine learning researchers who, they like to write MapReduce programs in Python. Or maybe at Duke, we have people in statistics department, they want to use R. R is a MATLAB-like language. And of course, people in the business analyst might actually want to use declarative languages like Hive, which is very similar to HiveQL, is very similar to SQL, or Pig, which is a more scripting kind of a language, which people, again, are much more comfortable with compared to an SQL-like language. Then there are workflow execution engines, because often you can't do much with just a single MapReduce job. You have to string a whole bunch of them together. Uzi is a workflow execution engine that can connect together a whole bunch of MapReduce jobs or Pig scripts or whatever into a large workflow. And now that there is a cloud, it's very easy to set up a Hadoop cluster on the cloud. And there are Amazon actually has this service, which makes it very easy. Within minutes, you can actually have a 100-node Hadoop cluster on the cloud, and shut it down when you don't want it, right? And Hadoop and these MapReduce frameworks are more accustomed to dealing with streaming workloads, or reading a whole bunch of data off disk and doing scan-based processing. But if you want random access, there are key value stores like HBase, which again fit in as part of this larger ecosystem. Okay? So Starfish is basically something that fits in here. And the two things Starfish actually brings are this emphasis on MADDER principles and self-tuning. So let me start by explaining what they are. And again, the way to understand these MADDER principles is, what are these characteristics of big data analytics? What are people actually trying to do, and how they want to do it? And similarly, or as a follow-up to that, what sort of features are people looking for in a system for big data analytics? Okay? And what is interesting is that we were actually thinking about this in 2009. And in 2009 VLDB, some of us attended, there was a talk given by Joe Hellerstein and his collaborators from Greenplum and Fox Interactive Media. They tried to actually come up with a similar characterization. Their characterization was actually kind of similar. There was some synergy between ours and theirs, and we sort of co-opted their name. But I'll actually tell you how our view sort of differs from what their view is. So the MADDER comes from magnetic, agile, deep, data lifecycle aware, elastic, and robust. So the M in the magnetic. So again, this is really what are features, what are the features people want from a system for big data analytics? They want a system to be magnetic. What that means is it should be very easy for them to just get their data in the system and start working with it. Okay? You can take the example of this journalist. So they have a bunch of data. They have absolutely no idea about the data. They don't know schema. They don't know if it's actually all clean and all. They just want to get it in, and only then can they start learning about data. So if you actually tell them, look, you have to do this whole bunch of things, schema, and identify all of these things about data, the data will never get into the system. Okay? Agile, and again, another feature of these big data analytics is often you're working with different data sources that could evolve. Things would actually change. So the system should be much more flexible. It should, change should be something that should be easy to do in the system. And what is often counterintuitive is that the less the system assumes about the data or the requirements, that system can be more agile. Deep, and this is actually one place where we differ significantly, or our vision is a broader vision of what Joe Hellerstein and his collaborators had. For them, deep was, people don't want to write joins and aggregation and these sort of things. That's just one part. They also want to do very sophisticated machine learning analysis and things like that. So for them, deep was the system should support such sophisticated analysis, and they were writing all of that in SQL because they were working with the Greenplum database, which supports an SQL interface. Our notion of deep also has a notion of broad with it, like an ocean being deep and pretty broad. And our idea is we don't want to go and tell the scientist or the statistician or the journalist, look, write all your stuff in SQL, and we know how to handle SQL. Rather, we want to go and tell them, look, you're comfortable with R, write things in R. Or you're familiar with using Python, do it that way. Or SQL, do it that way. And we want to do our best, given whatever language they are actually comfortable with using. Okay? The next three are actually things which the Joe Hellerstein and his colleagues didn't have. And the next D stands for what's called data lifecycle awareness in the system. And it's best illustrated with an example. Most websites that you go to, and actually the way they make money, is by having very sort of customized advertisements or recommendation of news articles that very likely the user might be interested in, is willing to click, or many other things. And the way in which these websites are actually generated, there's a whole bunch of analytics that actually goes behind them. The web page I actually showed was of Yahoo, but this holds true for Yahoo or Facebook or LinkedIn. I've actually taken an architectural picture that LinkedIn actually posted in a blog post. So this is a system that drives part of their website. And if you look at the system, there are three aspects of it. One is the entire data serving component, the web servers, all of these application services, the databases, and the newest, the NoSQL databases. Voldemort is a NoSQL database that LinkedIn actually uses, a key value store, if you want to think of it that way. And then, so this is basically what the user is actually interacting with. I go to LinkedIn web page, I actually do something. There is a log, not a database transaction log, but a clickstream or some activity information. That's all collected and moved into some analytics framework. In this case, it was Hadoop. This picture is like 2 years old now. People have moved on, replacing Hadoop with HBase or doing fancier things on that side. But the data gets moved into an analytics system, And then that's where all the analytics sort of gets crunched, and the results get moved back into the front-end system. So there is an interesting data cycle actually going along. And what LinkedIn says in their estimate in 2009 was terabytes of data actually moving through the cycle. The reason I showed this is basically data has these interesting life cycles. Okay? And people, and again, as I said, big data analysts have to support such cycles. So if, for instance, if you spend all of your time building a system that can process queries in like a minute, but it takes 30 minutes to get it in, that system is probably a non-starter if your cycle latency, the sort of latencies you want, was like 15 minutes. I would rather prefer a system that takes 1 minute to load the data in, but might require 10 minutes to actually process that data. So these are the things you really need to think about. Then the E stands for elastic, and the cloud is actually taking on big time. You may or may not believe in the cloud, but one thing people like, and especially the journalists, and I'll tell you why, they like is they expect the system to actually use resources and incur costs only proportional to its actual usage or what workloads it runs. For these journalists, their workloads are not like running. So you can actually think of two types of workloads. The Googles and the Facebooks and the Yahoos often have a lot of jobs. They have run periodically on the daily data, on the hourly data, on the weekly data. These guys actually, when the Obama administration releases a whole bunch of information about funding, that's when these guys' work start. They actually are analyzing the data. Or WikiLeaks releases a lot of data. So they expect the system to actually use the pay-as-you-go aspect of the cloud. And the last R is for robustness. Anytime you are actually running these big systems, even if you are running Hadoop on Amazon EC2, there are a whole bunch of challenges that will actually come in. DNS will actually fail, or systems will actually crash. A very interesting challenge is data actually getting corrupted. And I'm not going to talk about it, but the main thing I want to emphasize is things are actually going to happen, and the system should not fall down because of these individual things. It should keep going on. But once we actually had an idea, so we want to build a system which actually follows these MADDER principles, right? What we realized is these MADDER principles are very much about ease of use of the system. And what they end up doing is they make it very hard for the system to give out of the box good performance. Because if you think about it, the magnetism and agility often come with the system actually not knowing anything about the data. You can actually load your data in. Only when workloads get run on the data can the system actually know something about the data itself, the scheme of the data and things like that. Okay? The deep and data lifecycle awareness, we want to tell people, look, you can write your MapReduce programs in R or whatever, or you can actually string together these large workflows. They are not decorative SQL. You have to deal with these complex MapReduce programs and things like that. For the elasticity and robustness, very nice mechanisms have actually been built. You can actually grow and shrink your Hadoop clusters on demand. However, what often is trivial or non-trivial is the policies. When should you grow your cluster? How much should you grow it by? When should you shrink it? These things actually become very, very challenging. So what we want to do in Starfish is basically have a MADDER system and also provide good performance automatically. The system can learn and tune itself. And that's where the self-tuning aspect really comes in. So that's the vision that we are actually going with. So in the talk, what I'm actually going to do is give you a better feel for what are these sort of tuning problems, tuning challenges that people are struggling with, and where we can actually help them. And I'll focus on, there are different things that we do, but to make the talk actually sort of self-contained, I will talk about two of these tuning problems. One is given a single MapReduce program, a single MapReduce job, what are tuning challenges that arise, and also tuning the clusters that are allocated to run MapReduce workloads. But really focusing on the first one, and then I'll actually give you some insights from experiment evaluation, and then conclude with some ongoing work that we are actually doing. So what are these tuning problems that we are actually talking about? So we tend to think in terms of this is one of the ways in which I got this question earlier, and why the name Starfish, right? Although this is in retrospect, we tend to think in terms of 5 categories of tuning problems, although they are all nicely integrated together. As hopefully I can convince you of that. The first one is just think about a single MapReduce job. And I'm going to show you there are tons of interesting challenges in how effectively, how efficiently you can run a single MapReduce job that's been given. And as I said, nobody runs, or most applications can't just live by running one job at a time. They actually, even if you're writing a SQL query or a pig script on top of a MapReduce engine, what actually ends up running under the covers is a workflow of these MapReduce jobs. And there are tons of interesting things you can actually do exploiting the relationship across jobs, the relationship between jobs and the data they produce, and the producer-consumer relationships and things like that. And of course, if you have a MapReduce workload that people are running, then there are interesting challenges that come in, like the data cycle sort of challenge I mentioned, or even this is something which we are not doing, but others are working on how do you take a whole bunch of users and all of their requirements and try to multiplex that onto a single Hadoop engine. There are interesting challenges at the level of the data layout, especially, as I said, people might be loading their data in without telling you the schema or anything like that, but there are opportunities to observe the workloads and learn about the formats of the data and things like that, partition it and whatnot. And finally, sizing the cluster to run the entire MapReduce workload. So I'm going to drill down into two of these to actually give you a better feel for the problem. And this might be, next couple of slides might be things you have already seen, but bear with me so that I get everybody on the same page. Often a MapReduce job that actually ends up running on a system like Hadoop starts its life either as a MapReduce program that a user writes. So what I've shown here is a word count program written in Java. I know you can't read it, but there are map functions the user writes, the reduce function that again the user writes with well-defined APIs, and then there's this boilerplate code that ties together or packages the map and reduce functions into a job that gets submitted to the cluster. Okay? And the way execution actually happens is basically, we have a MapReduce program that is connected to a data on which the program should run and the cluster resources on which the job will actually end up running. And there is a configuration which I'll elaborate on in a moment. So once the job sort of gets packaged together, the first thing that happens is for the data, logically, different splits of the data get identified, and a map task processes each of these splits. Okay? And map ends up reading the keys and values from the input data, doing its map computation, sorting, partitioning, and all of that for the output key values, and then writes its output. Okay? So a wave of map tasks can actually end up running. Reduce tasks actually get started at some particular point. They will copy the partitions from the map output. Similarly, and the reduce will actually do its own computation. The entire map computations might run in multiple waves. We are actually processing a terabyte data set, right? The number of maps can easily get into the 500s to thousands range. And often your cluster doesn't have enough capacity to run all the maps in one single wave, so multiple waves will run. Similarly, multiple waves of reduces can actually run as well. And what is interesting in this whole exercise is basically we started off with a program and some data and some resources, and that got translated into an execution where a whole bunch of choices got made. How many maps? How many reduces? And there are interesting things like, the maps are internally reading and sorting and sometimes doing pre-aggregation on the data. Should we run the pre-aggregation? Should we compress the map outputs before they are getting shuffled? All of these choices on the reduces. A whole bunch of choices, and this is a quick laundry list of some of the choices you actually have to make. And it's interesting, who makes these choices, right? In Hadoop today, all of these choices have to be specified as a vector of configuration parameters that is given at the time the job is submitted. And that's what goes into the configuration C. So do these configuration parameters have any impact? Does it matter if I run the job with 1 reducer versus 10 reducers, if I compress, if I don't compress? So this is just a quick, we have spent many dollars on Amazon EC2 actually studying all of these things. Many is actually really many, like the big data thing. So this is just one quick example to illustrate the sort of the challenges that people might actually be facing who are running these MapReduce programs. So what I'm showing here is just 2 of these parameters, and I'm using names in Hadoop. You can think of this parameter as the map side buffer. So the maps are actually reading data, and they're actually filling their output data into a buffer, which is where the data gets sorted, partitioned, and pre-aggregations might actually done or even compressed before being written out to disk. So it's that buffer, and the other one is really a parameter that most people who have used Hadoop probably haven't heard about. It's actually a parameter that controls how much of this buffer to use for storing metadata, because these keys and values in this MapReduce world are, they're not fixed length. Right? They're text and whatnot. So there is some metadata that has to be stored. And what you can see and what is shown on the y-axis is we set these parameters to different values on these x and y-axis, and what's shown on the z-axis, the running time of the job. It's the same job, same data, same resources, everything, except I'm varying the configuration. And you can see that the surface is not so simple. Ideally, we want to set the parameters such that the performance is in this blue and good region, but it's quite easily, in this example, it turns out the default parameters setting with Hadoop can be really bad, and what's even worse is the techniques that people use to set parameters, the rules of thumb they use kind of end up hitting a really bad red region. Okay? Is there a question there? I'm sorry? Yes. So most of this work has actually been running experiments, learning about the real challenges, and then trying to see what we can do about them. Okay? And I'll actually tell you why that is the case, with, and hopefully also give some intuition. This is, these two snippets I've actually cut and pasted literally from the to-do list or the roadmap page of Pig. Okay? And Pig is a SQL-like, not so much SQL, but more some combination of a decorative and procedural programming language on top of MapReduce, which is very heavily used at Yahoo, and I'm sure in other places too. So what they're saying, and you can read it as well as I can, there are all of these configuration parameters that affect, and the thing is, if the same setting of configuration parameters work for all jobs, there's no problem to solve. But that's not the case. And the last part of this first blurb here actually shows how people go about dealing with this problem today. And what is shown here is a rule of thumb that people use. And that rule of thumb actually says, if your MapReduce job does not have the map part, does not have memory-intensive operations, and there is a combiner possible, then set this parameter to a high value. And the idea being, if you set it to a high value, then you can actually end up buffering a lot of data on which the combiner operation can be done. And the combiner is a pre-aggregation step that happens on the map side. And you can make it very small so that the spills will all be small. Things will actually look well and good. But this very rule can backfire big time. And rules of thumb are rules of thumb. They will work for some settings, they will not work for the other, and I'll actually tell you exactly why this rule fails later on. It's this sort of a rule that ends up leading to poor performance in the previous slide. The second part I want to emphasize on this, based on the second blurb here is, ideally what we want is people, the business analyst or the journalist, they shouldn't be thinking in terms of MapReduce jobs. They should be thinking in terms of whatever programming language is comfortable for them, right? And if I write a Pig script, I have no idea how many MapReduce jobs or what MapReduce jobs will actually get generated. So how will a person who's writing in Pig even know things enough to be able to set all of these parameters, right? They don't even know what jobs will get generated. So these are the sort of challenges that come in when you're dealing with jobs or like workflows, because as I said, Pig ends up generating a workflow of jobs. And we are now, so most of our work has been on, sitting at Duke and running experiments on Amazon EC2, but over the summer, we are collaborating with people at Yahoo to see whether Starfish can actually benefit the real workloads and real users at Yahoo.
Sort of a high-level
Yes.
question, I guess. There's, one way is to take all these parameters as a given and try to optimize their setting and automate their setting, which is what you're working on. But another is to, the original designers of Hadoop sort of threw the problem over the wall and exposed these parameters and said, set these and we'll do our best. You can imagine that the system might be changed so that it dynamically adjusts the sort memory relative to the map memory by sort of watching what's being requested and not.
Definitely.
So rather than assuming these parameters are fixed once and for all for the entire job, could Hadoop itself be changed? How much should we be optimizing what Hadoop has provided, and how much should we be changing Hadoop to do it right?
So the question was actually, and no, and I thank you for that question, because it gives me an opportunity to talk about how we came to where we are. Okay, thanks, Bill. So the question was, why are we dealing with so when Hadoop is a young system, right? And you can actually connect to database systems 30 years back, right? When basically these systems actually start, it's very easy for the developers, who don't know how the system will get used, to just throw in a parameter, because they'll say, I don't know how this parameter should be set. It should be set based on the workload, so somebody will figure it out. But the reality is, that ends up becoming, and databases, like people complain that they have these tons of tuning knobs and they're very hard to tune. So the Hadoop can actually end up going along the same path, right? So instead, why expose these parameters? One approach that could be taken is the parameters are internal. The system will automatically observe the workload and set the parameters. That's exactly how we got started on this project. That's precisely what we want to do. And as I was telling earlier, the name Starfish came from, Starfish is a very adaptive organism. So we wanted to make Hadoop adaptive. Okay? That's still something we actually want to do. There are a couple of things I want to say. One is, these parameters are fundamental decisions, so they are not going to go away. Somebody has to make that decision. Is the system making it internally without exposing it to the user, or the system can do it internally and also expose it to higher, very expert users? That's all choices we can make. And what I'll be describing can be used, and that logic can be put inside Hadoop so that the same adaptive thing, so users will not see it. Okay, map site in a buffer, that's you have to have it.
But you don't have to, it can change
Exactly.
during the job, maybe. But the Hadoop right now cannot, because you set it once for the job and that's it.
Exactly. So that is what I was getting to. So making things adaptive is definitely something we can actually do. And if you see, we are talking about self-tuning. And the goal is to Starfish will hide that logic, so users will not see it. And Starfish plus Hadoop will be self-tuning. Right? Users will not see those parameters outside. And the other thing is, quickly I realized when I started giving some of the initial talks to Facebook, people, it's very hard to convince Hadoop developers to actually make large-scale changes. So we can take two different research paths. One is where we say, look, if you make these changes to Hadoop, then you can do all of these smart things. The other is live with the constraints that Hadoop actually poses. So to get something out there and be useful, and I have actually spent, I shouldn't probably not be saying this, but I have spent a lot of time in adaptive processing. That's actually what I did my PhD in. And it was a big disappointment to see that just fall on the side. Led to sigma papers and everything, but was not adopted at all. Because these database systems, that was in database systems, they are so complex, it's actually hard to put a new logic in there. Right? So there are, when we start talking about the engineering and things like that, things become more sort of, I guess I would say, even political. Sorry. But we definitely want to go the self-tuning route, and I completely am on board with being adaptive and hiding these parameters. Any other questions? Or okay, so that was the job parameter and tuning part. Now let me actually tell you about different, just go all the way up to the entire workloads and sizing clusters for that. So one very nice thing that the cloud actually sort of, I would even say, is a revolution. Earlier, if I had to run, if I had to allocate like 50 nodes or 100 nodes to actually run something, I would have to go through a very long process where I would contact my system administrator and say, look, I have this project that is coming up, and allocate 50 nodes or 100 nodes for me. That could take a long time. Maybe if the nodes are available, maybe a couple of days to months to actually buy those resources. With the cloud and with Amazon EC2, we have a luxury of sort of choices. I can go to EC2 and within a minute allocate 100 nodes and actually have Hadoop installed and start running things on them. But what the so again, the cliche, as the cliche goes, right? With great power comes great responsibility. Which sort of means, now, as a user, I have to choose from among, like Amazon EC2, what I'm showing each row here is a type of node that I can go and rent on Amazon EC2. Smalls, largest, the extra large and whatnot. There are around 11 different types, not to mention auction-based allocation, things like that. If you see here, the first three, the second, third, and fourth columns actually show the resource specification of these nodes. And they are often, not, because these are actually virtual nodes, this can be some abstract number, like 20 EC2 compute units in a C1.extra large node. Or the I/O performance is high, right? So how can a user, and in each of these nodes, of course, comes with a per hour cost. So suppose I'm a user who has to run a workload, right? There are, what type of node? How many nodes should I allocate? So what we are actually showing here is, again, a real workload being run. The x-axis actually shows the node type, and all the number of nodes is actually the same. And the y-axis on the first graph shows the running time of the workload, and the second shows the cost incurred to run the workload. So if you just focus on the things shown in the box here, the extra large node can run the entire workload in like 2 hours, and these are batch workloads. So sometimes the user might be fine with the workload completing by 6 a.m. Eastern time in the morning, right? The C1.medium node takes 4 hours to run the workload. However, the cost of running things with the CM.medium nodes is 40% less. So these are choices that people will have to make, and in some sense, administrators were helping them with these choices earlier. So hopefully I've convinced you that there are interesting challenges that people who probably don't have expertise with Hadoop might actually be struggling with. And in one slide, I'm going to show you the way in which we actually go about tuning and self-tuning for these things. So we have 3 components in Starfish, and they can work at any of these levels. One is the profiler, and the one, short description of the profiler is, its job is to collect concise summaries of execution of jobs or workflows or workloads, run it, observe, okay, and generates these profiles, because as I said, we might be dealing with black box MapReduce jobs. Those profiles can be used by a what-if engine. This really is the heart of Starfish in a sense. And it can estimate the impact of hypothetical changes. For example, you can ask it, look, this job, here's the profile when it ran with 20 reducers. What will happen if it ran with 50 reducers? What will happen if I turn on map compression and the data size were to increase by 20%? And even things like clusters. If, what will happen if I change the production cluster from 10 C1.medium nodes to 4 C1.4 times extra large nodes? And there's a set of optimizers that we have written for each of these different tuning challenges that actually come up. So the job of the optimizers is to search efficiently through a space of tuning choices. In the case of job parameters, it would be the high-dimensional space of job configuration parameter settings. In the case of cluster sizing, it would be nodes, node types, and actually Hadoop configuration on the nodes, and make appropriate calls to the what-if engine, sometimes creating profiles and invoking the profiler. So these 3 modules, in combination, help solve these challenges. So this is the very short, summary, one-slide summary of the approach that we take in Starfish.
How many parameters do you have?
So Hadoop, I think I didn't mention it. Hadoop actually has like 190 parameters, but around, most of them are where should I write the log files to and things like that. Around 20 to 25 parameters can have significant impact based on the workload. We currently work with 14 of them, which by some initial studies we have identified are the crucial ones. And we have also, those are the job-specific ones. There are parameters that control at an internal level across jobs, how performance can actually be. So we are not working with them, like the file system level settings and how many threads should the file system have and things like that. So we are working with 14 of them. Okay. So based on the previous slide, hopefully the Starfish architecture slide makes sense. There is a profiling layer. So we actually think about jobs, workflows, workloads, data. Okay? And at the workload level, that's where we talk about the cluster sizing aspect too. The elasticizer is actually our cluster sizing component. The profiling and what-if engine cuts across all of these layers. And now I'm going to drill down into the MapReduce job tuning problem to again give you a better feel for what these profiles are, what can the what-if engine do, how does it go about doing it, what is the optimizer actually looking like, and things like that. So abstractly, the problem definition is the following. Given a job which connects program, data, and resources, we have to pick the best configuration. For some metric, maybe it's job completion time. In some cases, it can actually be I'm running a lot of jobs, so I want to actually get good resource utilization. I don't want to. It could be that if I have 1,000 reducers, the job's completion time can be really good. But if I have 500, it is equally good. But 500 reducers means I'm leaving the remaining ready slots for other jobs. Right? So the metric can actually be different. For now, just think of it as the completion time. Okay? A bunch of challenges that come up. So we have our 3 components. So the way we go about doing it for this particular problem is it's a job of the profiler to collect a profile for a job which has the same program, but it could be different data, resources, or configuration. So we need a profile to start off with. And right here, you can actually see a difference between SQL and what database systems actually do, because database systems can estimate performance of a query execution plan without it having been run before. Right? We can't do that, although when we work at the level of PIG, we are actually finding ways to generate profiles automatically based on data statistics and things like that. I'll be happy to talk about that offline. For now, we are dealing with black box MapReduce programs, maybe written in Python. Right? So we need a profile. But there are interesting things that Starfish actually supports, like if you give me a job that has to be run, I can run a sample version of that job. Just run a few maps, few reducers, and collect the profiles. And I'll actually expand on that. Okay? Given a profile, the what-if engine can then answer any question for different data, resources, or configuration. If it's the same data and resources, you're asking questions about different configurations. Optimizer enumerates the space, makes calls to the WATF engine with the profile, and finds a configuration to recommend. That's how things work. Let me tell you about what does a profile look like, and we have actually spent, I think, a good bit of time here. I'm very happy to talk about that part. A profile is, at a high level, concise representation of a map-reduced job execution. So what does it contain? What is the information that it contains? So it contains information at the level of tasks and phases within tasks. Okay? So if you look at the map, this is an execution at a high level of a map task. If you look at it, the execution internally consists of reading input data. The splits I mentioned when I showed the example figure, from that key value pairs actually come, and the map function gets invoked by the framework. And this map function, you can write it in Python or Java or whatever language, right? And then the output is get put in the buffer. This is the IO_MB buffer I was actually talking about. And there are rules on when it fills up to a particular threshold. You can actually run the sorting of the data, combine the pre-aggregation, and writing it off to disk. And it could be that the data size is such that you actually spill to disk many times, and then all of them have to be merged together to make the output data ready for the reducers to pull. So there are a lot of phases, and we actually model or collect information at the level of these phases. What type of information? There are, at a higher level, there are two types of information we collect. Data flow, how many bytes are actually being sent, or how many merge rounds are actually happening, as well as time or cost information. And for now, this information is collected as how much time is being spent in each of these phases. Okay. So a quick, this is a screenshot from the Starfish visualizer. So based on a profile that was collected for a job that had around 326 maps and 27 reducers, based on the data flow and cost information, you can actually plot, you can visualize information in this fashion. These are the maps, the map running times. These are the reducers. Right? So this is like time-based information at a high level. You can actually visualize data flow information across tasks from maps to reducers, or you can actually aggregate at the level of all the map tasks from this node to the reduce tasks that run on that node, how much data actually went through. But you quickly realize that there's a lot of data. 1,000 maps, 500 reducers. There's a lot of data. So we probably now want to start thinking about the summaries of the data, or the statistical distribution of the data. For example, of all the map tasks that ran, what this is actually showing, and you can't read the these things here because it's a screenshot. So what this is showing is some map tasks ended up sending, some fraction of them ended up outputting around 22 megabytes of data. Some of them ended up outputting around 45 megabytes of data. So you can start visualizing things to the level of those underlying distributions, because there are all of these fields that I'm talking about can be collected at the level of each and every task. So there's a nice distribution, and you can actually think about the running times at the at the phase level for some sort of an expected map task or expected reduce task. So slowly from that big blob of data, you can actually extract nice statistical properties of the job execution. And that's exactly what completes the remaining part of the profile. So the data flow and cost are more like raw data and just simple aggregations on top of the data. And then we extract. For example, for every map task, it actually read some amount of input data, output some amount of data. Right? So there's some selectivity we can talk about. And now we have, if 1,000 map tasks ran, we actually have 1,000 of those points. Right now, for the most part, in the implementation that you can actually download, we are working with the expected value of these distributions, and that's what is used by the WATF engine to make its recommendations and things like that. We are working with expected values of all of these things. At the cost level, there are things like how much time was actually spent doing local I/O per byte or per record. So now the question that comes up is, so that was the profile roughly, right? Data flow, cost, and more aggregate information and statistical information. So where do these profiles actually come from? They come in Starfish in two ways. One is measurement, and that's the job of the profiler, and the other is through estimation, and most of that is done by the WATF engine. Okay. So let's look into how profiles are generated through measurement when a job actually runs. So here again, the same question that Bill actually had brought up on, we could actually collect these profiles by going in, changing Hadoop, and adding a lot of instrumentation, things like that, into Hadoop. But my feeling is that would be a non-starter. Instead, what we have done is we impose two requirements. You should be able to collect these profiles with 0 changes to Hadoop code, and 0 changes to the user, like when the user is writing a MapReduce program in Python, I don't want to tell them, look, add all of these things and then I can profile. 0 changes there. Okay? So what's interesting is now that we are able to do this, and we actually gave a talk at Yahoo, so then the Hadoop people are actually realizing, if you have these things, you can do many smart things. So maybe it's a good idea to put them into Hadoop. That's probably the approach if you want to have some real impact. Things I'm learning, over time. Anyway, so what we do to support these two goals is an idea called dynamic instrumentation. This is not something we came up with. It's something that is used heavily in programming languages, in things like bytecode analysis and reverse engineering and things like that. But it fits really well. At a high level, what dynamic instrumentation means is you write some event condition action rules. These events I'm talking about are events at the level of a program execution, like a function entry, function exit, exception being thrown, or a timer event actually coming up. And for these events, if some condition holds, take some particular action. You can write these rules, and what happens as this thing actually just came up, dynamically, the corresponding bytecodes will get generated and get put into Hadoop execution code so that we can collect the information. Once we are done, it just goes off. Okay? So we can achieve both of these goals. And we use a tool called btrace, which is not probably the best. It has overheads, but we learned that over time. Okay? Now let me pictorially show you what I was actually talking about. So we have our MapReduce job execution that's happening, and Hadoop is completely in Java. The framework is in Java. So when a program is being run, the slave nodes will spawn these JVMs, the Java virtual machines, inside which all of those map task execution, the figure I actually showed you, will actually run. If the map program is written in Python, this will actually funnel off a call to a Python process that will actually run the map function, but the Hadoop execution sort of remains unchanged, right? Now, whatever we want to profile, we have these event condition action rules that are written again in Java, and what will happen when we turn them on, automatically they will get compiled. The bytecodes will get added into the bytecodes that run in Java, and the fact that Java is actually it's basically there's a virtual machine as being interpreted actually helps a lot here. So suppose we wanted to measure, let's say, the time being spent in the map function as opposed to the time being spent in spills, like what I was showing in those profiles, so that we can optimize parameters appropriately. We inject these in the right places. As the code runs, our actions will sort of get called. They can measure times, they can measure the data flowing through, write the raw data, and there's an increasing or a sequence of aggregations and statistical data extraction or property extraction that happens to generate the profiles. So this is roughly what happens. Actually, I have a question. Do you have a question? Okay. Yes.
So this is just to make sure I understand. So you have the btrace engine, and you're going to write rules of the form if this binary calls function called map, then starts timer or something like that, right?
Yes.
And ends that function of that name. So the rules are going to be specific to Hadoop.
Yes.
But they're going to be written separately. And in what language do you write them?
So the rules are actually very, I get these buttons wrong because they are backward. Okay. So the rules are themselves written in Java. So what btrace is, and there are other tools like this. You can write these event condition action rules in Java, and those events are very specific to Hadoop code, which in some sense is a problem, because now if I change the Hadoop code, then I'll have to update the rules. Although we are talking about really core parts of Hadoop which haven't been changing that much, but that is definitely a problem. And what ends up happening is, essentially the bytecodes will sort of get generated and injected using the same, the bytecode, like Yangshil was telling me about some of the work that you guys are doing, right? That technology remains the same. But there's a lot of engineering that people actually do, and companies make their living off of Java instrumentation, where you can btrace is an open source tool. It's very slow. You can run. Okay. Let me take a step back. So btrace is basically a tool where once you write your event condition action rules in Java, it will use JVMs, a very specific interface it exposes. I think it's the instrumentation API, pure Java instrumentation API. Use that to sort of create these agents which are plugged into the JVM, right? There are ways in which you can do that entirely in C. The agents are written in C, which can be much faster than btrace. So a lot of interesting things over there. I'll be happy to talk about it offline. Does that answer your question? Okay. Yes.
So everything, well, actually inside of MapReduce and everything happens in pipeline. How do you combine those, so you're collecting the statistic for each phase, where
So the point, that's again a very interesting point. So in reality, although the way I show these faces, it seems like they're a very nice sequence of things happening, right? I give it to the map function that puts it there, and then things happen. But the reality is they're all threads, lots of threads inside, inside the JVM, which are doing these things in parallel. So that's the problem we have to deal with. Again, there's no silver bullet. We actually collect times and do an appropriate correlation to put that picture together. And the real other part of the answer is how accurate you want that information to be depends on what you want to do with it. To tune parameters, most of the time what we need at that level is in a relative sense, how much time is being spent in the map with respect to relative spilling, with respect to combiner, with respect to compression, so that we can figure out, oh, for this job, combiner is a bad idea, turn it off. Or for this job, you actually want the combiner but no compression. I'll show you an example of that. So the granularity at which we are collecting data is good enough for that purposes. But if you want a very detailed picture, it gets into, there are many threads and function calls actually going through. How do you attribute time appropriately?
This is kind of related question. So Java used JIT compilation.
Mm-hmm.
So does that somehow affect your measurements, or how do you handle the dynamism? Because every time you insert some instrumentation code, that will get first get compiled, and so with JIT compilation, the longer you run your same code, will get more performance. So
Right. That again is basically, that again is a problem that we have to sort of deal with. For now, the part is we are sort of punting the problem to btrace. So we are just assuming btrace does the right thing, but there is definitely the fact that where people are sort of reusing JVMs and all of these things in MapReduce, you can actually get good performance that way. Again, my answer would be that's a real problem that we have to deal with. For now, when people profile, they're trying to get an idea of these relative times, and all of those JIT-based compilation tricks will improve performance. That can always happen, right? I don't think it's really a question of, the sort of the parameter that we are talking about, combiner or not, spilling, what is the size. These things are not really affected that much by JIT. If you had a big map function that's doing a whole bunch of things, that would be something the compilation and then inlining or whatever can actually help with. So those are not the place where we are playing our games. Okay, any other questions? Well, okay. When somebody sees this sort of a picture, the immediate question is, so what happens? How much overhead are you adding? Like you're adding extra computation, there's I/O that is happening. So that's definitely again a challenge. The slowdown that the task will actually experience because of our profiling. And there are two modes we actually support in Starfish to be able to deal with that problem. The first thing is, well, both of them involve sampling. The fact is you're running thousands of maps. You don't have to profile each and every one of them. Right? You can basically profile just 10% of them. I'll show you results and get very good results for the optimization that we want to do. So you can actually run. So here this task is not being profiled. And even better, we can actually mention the sample job version. So we can automatically take a MapReduce job just before it's going to be run, change things so that a sample version of that, meaning a sample of the map task and some number of reduced tasks actually get run. So that that way we can like before a 1 hour job is going to be run, like we can spend 2-3 minutes or even 5 minutes getting a good idea of the profiles, then use that in the optimizer and run a better version of the job. So we support both of these modes. That was the profiler. So now going back, the problem of the WRF engine, we have a profile that was actually been given. The job of the WRF engine is given some possibly hypothetical, same program, but possibly different data. This could be a sample, this could be a full data, or this could be yesterday's data, this could be today's data. Different resources, maybe this was run on 10 C1.medium nodes, and this is 5 C1.extra large nodes, or a different configuration setting that was run with 10 mappers. This is being run with 100 mappers. We want to estimate the properties of that hypothetical job execution. So what we really want is, without running that job, we want a virtual profile for that, because we have our ways in which, given a profile, which is a summary of the execution, we can sort of simulate that execution, maybe individually, maybe with many other jobs that could run together, and actually estimate what the real execution will be in terms of how much I/O will it actually do, how much resource utilization will happen, how much time things will take to run. So the crucial step is this one, generating the virtual profile. Okay? So for that, and again, this is something which we have probably spent many, many, many months on, and I'm going to show it in the insights in 2 slides, but I'll be happy to talk about offline. You can check out the code too if you want to. So this is the problem that we have to solve. Given the profile, and you can think of the profile in the given job as these 4 categories. Data flow and cost I mentioned, these are really aggregate, raw data, not very useful. We have taken our statistics. Based on this, we want to estimate the similar fields in the job without running it. Right? That's the problem. The first part is like the data flow statistics here to the corresponding data flow statistics in the other job. Here there isn't too much room to innovate, meaning if, for instance, if I know that program is actually a joint job coming from pig, and I have statistics about the data, then I can estimate things like if the data size were to increase by such and such fraction, or if you give me a different data set, how will the data flow statistics be? There isn't too much you can do except that if you might be able to generate that same information based on static analysis of the code. What we end up doing for this part is use pretty simple cardinality models of the form. If that, maybe without any information given to us, we make what we call a data flow proportionality assumption. What that means is the size, because if it's a data residing in a file system, all you can reliably estimate is the size of the data, right? If the size is all of these individual flow, that's the fields that are their values are proportional to the size of the data. That's our very fundamental assumption. Surprisingly, it works a lot of the time because a lot of the use of Hadoop in these companies like Google and probably not Google, Yahoo and Facebook is really about extract transformation logic sort of a thing. You get all your click streams and everything, and you're doing a lot of processing on that. And those pipelines tend to have a very good data flow proportionality nature because today's data very much resembles yesterday's data, right? But what we are really doing here, there are 2 things we are doing now. One is we are actually building what we call a Hadoop profile sort of warehouse. So the idea is profiling is always on for every job that runs, so it's sample-based profiling. So we actually can observe for the same program multiple runs what really happened, how much data actually went through, so we can train black box models. But when we are working with the big folks at Yahoo, really it looks very much like what the cardinality estimation that databases actually end up doing. So where we have innovated is this other part. Now, if you change the cost statistics are very much a function of the cluster, the node type, the amount of IO and the network resources you have. There, to solve that problem, we have come up with what we call relative black box models. So relative black box models, I'm going to illustrate that in the next slide. So the problem is, given let me simplify. So essentially, if you tell me about how a job ran on one cluster, I can answer how it will run on a different cluster. And our secret sauce is, before you ask the question, I will take a benchmark of, in this case, MapReduce jobs, run it on both clusters, and observe basically if the same job run on this cluster, run on this cluster, how do these, in this case, we are talking about the cost statistics fields. How do they behave? And we build what we call a relative model, such that next, if you give me a different job and give me the statistics for when it was run on the source cluster, I can use that model I learned. It's basically a black box model. We use regression trees, actually like a suite of regression trees because there are many fields in here, and I can predict it. That's the, yeah.
So in this approach, do you scale each parameter separately? Do you have like a model for each parameter? How that parameter scales in the new cluster?
So here the parameters we are talking about are the fields in the profile.
That's right.
Yes.
So is there like separate one per field?
Exactly, yes. In fact, the cost statistics, there are around 20 fields in there. They are not really fields strictly. They are distributions of IO cost and these sort of things. But for now, we are just getting the mean value of that. And we build a model given the 20 fields here, and all the runs across these different jobs, a model for each field in the output. But I want to clarify one thing is really first thing we thought was really the accuracy is going to depend on how good of a machine learning model you have. But really, what it really depends on is how good of a benchmark you have actually selected. And we have come up with 3 different approaches. I don't have time to talk about it, but the brief insight is you could actually think about, let me collect a sample of jobs from the actual workload that's running. Okay. Or I can come up with jobs that, I know that will stress different resources, like sorting will actually stress the IO a lot, and then the word text analytics will actually stress CPU a lot. But what we found is a very sort of is really counterintuitive. It's basically a small set of jobs, like 2 jobs, that what they will do, they're synthetic jobs. But when the jobs run, the different tasks in those jobs will simulate different types of execution, like CPU intensive, IO intensive, generating a lot of output data, generating very little output data. And so based on just a few runs, we can collect all of this data. But that's a separate discussion. I'd be happy to have.
How many total jobs do you sort of have in your hands to be able to train these models with? You counted up everything.
So the real answer is, if you're actually doing this for Yahoo, I'll actually probably suggest taking a sample of jobs from Yahoo, right, for my first type of benchmark I mentioned. But the technique that we have, this will be presented in the cloud computing conference that's coming up. Basically, independent of what jobs you run, because really we are trying to learn properties of the Hadoop execution, right? You can come up with synthetic jobs that will behave like a small category of jobs which are CPU intensive, IO intensive, writing a lot of data, things like that. So the short answer is, what we have is now fairly independent of what workload you're actually running. Of course, we'll generate data and model parts of the space that you probably don't need based on the jobs you end up running.
But if you did have Yahoo's entire trace for everything they run, could you just run it through a model and
Definitely, right? So
it would be a reasonably high quality.
Okay, so again, sorry. So the question that Bill was asking as well, and again, I think it really gets at this, like how do you pick these jobs? So if I had a workload that was consisting of 10,000 distinct jobs that are being run at Yahoo, does that mean we have to actually pick a significant fraction of those 10,000 jobs, or can something actually be done here? So the first answer I gave was actually the technique that we have come up with, which unfortunately I'm not talking about, can address the problem. Is independent of the number of distinct types of jobs you're running. But then Bill actually brought up this other point. Look, earlier I said we're actually talking about a Hadoop profile warehouse, right? If we manage to solve the problem of very low overhead profiling of these tasks, and continuously every time a job runs on these clusters, and these 2 clusters often in the context of Yahoo will actually be a development cluster where people initially try out their jobs before unleashing it on the big production cluster. So those will be the 2 source clusters at a place like Google or Yahoo. I can collect these profiles from real runs of the jobs, right? And then I can do this entire thing based on offline from this performance data warehouse. Yeah. That's another reason why we are actually moving in that direction now. Okay, so that's basically the little black box models, and then we have done work on understanding Hadoop execution and the MapReduce execution to develop more custom analytical models, like they're really mathematical functions that can take the data flow statistics, for example, connected with the configuration like the iostar.mb, and really predict what the data flow will be. And remember that data flow also includes things like how much data will be written to disk and things like that. And then white box models that can take the cost statistics, the actual data flow that's running through, and the configuration to really estimate the times or the real cost of the execution.
I'm a bit confused now. So what is the difference between the cost statistics and what comes from the right?
So the cost statistics are, the cost statistics and data flow statistics are more like, they are, well, in this example, you can think of a cost statistics field will actually be the time you spent doing I/O to the local system per record or per byte. Okay, I have to mix that with the total amount of data that's actually going through to come up with the total time you'll actually spend, right? Because those are the ones you can use to compare. You need things like the cost to really compare. If your metric of optimization is the completion time, you need this to compare 2 different configurations. So that's the idea.
Another question. So here, now that you have the data flow estimates and the cost estimates, is your final white box model kind of more Hadoop specific in the sense that you know how Hadoop is going to actually run the job and schedule different tasks to figure out exactly how the runtime will look like?
Definitely. So the question was, are these white box models, if I'm using the Hadoop system as my execution engine, are these white box models specific to Hadoop? Yes. But the way we have at least tried to write the code is to make all of these things modular. If you plug out Hadoop and replace it with a different MapReduce execution engine, things will still work, although that's...
Because kind of what we
Right. So actually, let me clarify one thing there. So the scheduler aspect actually comes in. Okay. So in a sense, these costs in the data flow are at some level single job specific and abstract representation. They are more relative than anything else, and those things are taken by the scheduler simulator to actually estimate the real running times. So those costs, although I mentioned they are real cost, they are at some level like abstract. Just an example would be in DB2, they use this notion of time rounds, which is their, when they're comparing plants, which is their abstract notion of cost. So those costs that we are talking about are, at some level, they are abstract, although the way we are doing it, they kind of map to real numbers. The simulation comes in because you actually now, if I give you a virtual sort of a profile to estimate completion time, remember there are many waves in which map tasks might actually run. So there are scheduling artifacts, right, when you run something on a real cluster. Plus, I might be running multiple jobs together. So those things are handled here. Okay, look, so one more final thing, and then I can actually start showing some experimental results. So the final part, job optimizer. So again, given a job profile and given the new job program on some data and resources, we want to find the best configuration for that, right? So this is really a search problem, right? You have to enumerate. In this context, it's basically a high-dimensional set of configuration parameters. We need a technique to enumerate that, make the what-if calls to actually get the cost so that we can compare things. So the time, one thing is like, the running time of these what-if calls, because of like the models, most of the models have been learned ahead of time, right? So just going through the models, that finishes in milliseconds. However, scheduling can push that time into the order of like, even a second. Larger your clusters, more map tasks, more reduced tasks there are. So the what-if calls are not that cheap, although I think they can be made cheaper. So it's important to keep the number of calls actually really small. We are dealing with, as Dan asked, like what is the size, what is the dimensionality of the configuration space we are dealing with. Right now it's 14 parameters. And 14 parameters, if you use some sort of a gridding technique, this can take a long time, right, to actually run. There are two sort of insights we have brought in to actually keep the running time manageable, the order of like 1 second, although it can go 100 node clusters, 500 node clusters. And these are really not the size of the entire cluster, but the size of the cluster on which the job is going to run. If you're running things at Yahoo, although you might be running things on a 2,000 node cluster, because of the capacity scheduler and things like that, you might actually be running on 20 nodes, 200 nodes. So each job may not run on that large number of nodes. The two insights that we bring in, one is we are calling subspace enumeration. Choose your subspaces such that there's independence across them. So the idea is that, like, many of these parameters affect map execution, many of them affect reduce execution, some of them affect shuffle execution. So I can carve the entire space of parameters into things that affect maps. So if I find a good configuration for that, I can pretty much use that configuration for the other spaces. The other parameters will not affect it, right? That can save enormous amount of time. And then individually within each subspace, how do you go about doing it? Simulate annealing and all of these techniques. We have tried many of them. The thing that we actually like most is what is called recursive random search. It's basically a sampling-based approach in that space. We didn't invent it. We tried it. We liked it. It's basically there's some good advantages. It has some theoretical guarantees behind it. Best thing is it scales very well in high dimensions, as sampling does. And once we cut things down into smaller subspaces, it's been working really well, although it's been very hard for us to find out the real optimal configuration. That will involve many, many different runs. At least in the small context where we could verify it, this is actually doing pretty well. Yes?
So instead of actually trying to find different configurations of parameters and making these what-if calls, have you thought of a way to define it as a constraint optimization problem? To say, this is my cost optimized in time, or this is, my time constraint optimized in terms of cost. So basically doing the thing backwards.
Yeah. So the way I would actually, so the question was, the way we are approaching things here is we come up with some sort of a model, right? And then from the outside we ask it, oh, what will performance be if I had 20 reduced tasks? Give me the value. Then we'll ask it, what will performance be if I have 40 reduced tasks? And then from the outside we convert it to a search problem. Instead, if it's all some set of nice mathematical models, why can't you just unleash a like why can't you just treat that as an optimization problem? I think we could probably do it because it's backward. This is backward. Okay, so these models are mathematical models, right? So if all we were dealing with was the same resources, same data, then we could potentially use the approach you actually said. But if you have, like, if my space includes like cluster sizing and configuration for that cluster, I don't think we can actually do that, because we tried this just to bring this picture. Took us around a year to find the right set of where to use black box models, where to use white box models, where to actually use simulation. It actually took a long time. Although individually these are all at the end they all look trivial. Just putting the entire package together. So that would be my answer. Although frankly we haven't looked into that deeply. Okay, look, evaluation, right? So the Starfish, basically we released the first version of Starfish, 0.1 version, early this year, and that is what was used in many of the evaluations that we did for the papers, some of the papers we have written earlier this year. Starfish, over the summer, we have actually been working, especially in collaboration with Yahoo, to take Starfish, make it, actually better in terms of. Our focus has been really features, adding more features right now rather than individual performance tricks. So the experiment evaluation that I'll be talking about sort of uses the versions 0.1 and 0.2. The setting that I'll be sort of using is again running Hadoop on EC2, on Amazon EC2. Okay. The scenarios like to evaluate a system like Starfish involve creating different cluster configurations, different workloads, and actually data. And the interesting thing is, for different cluster configurations, I can produce a cluster configuration where Starfish is able to beat the rule-based optimizers and everything by by a big fraction, right? But in a different cluster configuration, maybe they actually match. So our I'll make some of these insights more clear. First of all, I showed this slide earlier. What is again showing us the different types of nodes you can actually rent on EC2, and in the evaluation, I'll be showing some results with the C1.medium node, which basically the way Amazon actually specs it is CPU. There are 5 EC2 compute units, so it's like 2 cores, 2 virtual cores, and each core is individually 2.5 compute unit each. Okay? So each compute unit is kind of like a wimpy core. It's like a 2007 model machine with 1 to 1.2 gigahertz. And I'll also show you some results with the CC 1.4 times extra large. So it's primarily meant for high performance computing. They're pretty beefy sort of cores. There are 8. It's a dual quad core machine, and Amazon sort of says there are 33.5 compute units. Okay? Memory sizes are actually fixed. I/O, you can again see, is more abstract. This has moderate I/O. This has very high I/O. And of course, the costs are also pretty high for them. It's $1.6 every hour. C1.medium is just 17 cents an hour. This part we are seeing here is the way Hadoop is actually run on every task node or every slave node that runs these map and reduce tasks. There are some fixed number of map slots and some fixed number of reduce slots. So if I had a 15-node cluster with a C1 medium cluster with, or a 15-node C1.medium cluster, then I have 15 times 2, 30 map slots. So my wave size is 30. So if I had 90 tasks, I'll have to run them in 3 waves. Okay, and then for every task slot, the maximum Java heap size, which is so all the the I/O sort of MB and reduce side buffers, they all sort of get carved off from this one. And this part is again, if you actually vary it, you can also get good performance. So we have done a whole bunch of experiments, and these are relatively good numbers for the type of nodes that we have come up with. Okay. So the workloads and data, we have tried to choose workloads from different domains, and these are all individual jobs. From natural language processing, there's this word concurrence program for which I showed you the response surface. There is sorting and joins from the more database style workloads. There is a workflow, a small workflow of 3 jobs: the term frequency, inverse document frequency, and we work with data of different scales. The smallest 10, around 30 gigabytes. This one is we are working with even 10 gigabytes, because word concurrence is actually what it's doing is it's taking a stream of sort of documents and then finding for every pair of words their concurrence. So this, even when you start with 10 gigs, it sort of blows up the data because it's doing a quadratic sort of thing. And another thing, we actually work with the sort of compressed data, because when data is compressed, it's harder for human beings to sort of estimate how much the data flow will be and tune parameters appropriately. And for Wikipedia data, like we're seeing around 5 to 6x compression. So if you start off with 10 gigs, really the maps are actually processing like around 60 gigs of data. So this is sort of settings. First set of results for C1 dot medium nodes. And as I said, this is a cluster of 15 nodes. Each node has these 5 compute units, so around 75 compute units. Small data sets, 30 gigabytes. And what we are actually showing here are performance. So we measure the performance of Hadoop in this default out-of-the-box configuration. We run a rule-based optimizer. So the way in which, as I said, the way in which these parameters, these are all for single jobs, parameters. That's why it's the job optimizer in the title. There are rules posted by Cloudera, which is actually a big, one of the leading companies in Hadoop world. There are rules actually that Yahoo actually publishes. So we have put together a collection of rules, and then it's really rule-based optimizer is really us, because most of these rules are actually guidelines. They don't say, look, if you have this type of workload, use this particular value. So it's us, and then the cost-based optimizer. So for the cost-based optimizer, what we do is, for the job, we run the setting using the rule-based optimizer, or the rule-based optimizer setting, collect the profile, give it to our what if engine and optimizer, and it comes up with the recommendation. We run it, and they're all repeated enough, so that these are sort of, I think, numbers averaged over 5 runs. So in our runs, we have actually not seen that big variations on Amazon EC2, but I should definitely admit that these are the only jobs being run on the clusters. Okay, so in that sense, there's only one user at a time. So what we're seeing here is the default. Default can be really bad, and that's one of the reasons why 30 gigs, if you want to show default for 1 terabyte, forget it. Here, see that we are beating cost-based optimizer is beating rule-based optimizer by a fraction. Sometimes like it's around 2 times better. Okay? Frankly, we didn't expect this, and the reason for things like this happening, and let me try to convey the insight. So what are the sort of things that might be hard to miss in a rule-based approach, and especially when you're dealing with these different types of nodes on Amazon? So what I'm showing here is for the word count job from the previous plot. We saw that cost base was twice faster than the rule base. So rule base setting is A here. The cost base is B. So I'm showing the profiles of the runs. Okay. So this is the map profile for A and B. This is the reduced profile for A and B. So this is the running time for the map task. So you can see that for our cost-based setting, managed to cut the running time of the maps by around a fraction of 2. Okay, so from 320 or 30, it actually came down to 160, 170. Okay, that's where we are gaining all of yes.
How can you reduce the time of the actual map function rather than the user-defined function?
Okay, so I should admit that I wasn't very clear then. So it's really this green. That's the time spent in the map function. So when I say profile, I'm talking about everything from, the map task, everything from reading the data, extracting the key value pairs, calling the map function. That is the green one. The map is the green one. Then the output comes out.
The green one's the one that gets a lot smaller.
Green, yes. Green one. Okay, your question was that. Okay, great. Sorry, I misunderstood your question. Okay, so essentially, now that is definitely as part of the story I'm actually going to tell. So maps are actually getting cut down, but reducers actually increase. So we actually investigated. So Dan brought up the question of why is it that the map function time here is basically around 100 seconds. Here it's probably around 40 seconds, right? So really what is happening is that in the rule-based setting, the rule base basically said, look, give these large IO.MBs, and then things actually get put in there, and comparisons, few spills will happen. However, combiner, things like compression, running the map in the functions, they're all consuming CPU cycles. So with the larger IO.MB, and remember, sorting is happening. Sorting is a n-log-n operation, right? That can actually make things pretty intensive. If you cut down the IO.MB, literally, the sorts will actually happen on smaller, the n-log-n will happen on smaller portions, and then the rest will actually get merged, like our database two-phase sorting approach. So what ends up happening, with the combiner, it was actually making these medium nodes compute bound, right? we instead, because we are actually seeing these profiles and working things based on the profiles, right? Saw that the cost-based optimizer sort of saw that, and it came up with a smaller IOStar.MB. What that meant is, more spills, more merges, more data shuffling getting shuffled across. However, we sort of sized it well such that although now the reduced times for B, our setting, increased. But if you look at overall, that is taking around 300, and this is running around on the order of 10 seconds. So overall, this is actually better. So these are the sort of things which you can do with a cost-based approach, which might be harder for like even manually or even with these rules of thumb to be able to sort of capture. Okay?
Are you going to show the performance of the model? How accurate the model do you think is?
I have some set of slides to actually show that in the talk, but I'll be like there are many more. Yeah, they're coming. So the way I'm presenting it is first the optimizer, the overall, then drilling down into profiling, and then into the what if. Okay, so this is basically so we started off with our 75 compute units. We sort of increased that to around 670 compute units by having these much beefier nodes and much wider in terms of number of slots in the cluster. And this is much larger scale data as well. So here you can see that rule-based optimizer is actually performing, or we are sort of rule-based optimizer is performing. I've dropped the default because it's just hard to actually put it in here. If rule-based optimizer is 1, how much are we doing better with respect to that? You can see that sometimes we are actually doing better, but there are cases now we are doing actually worse as well. Okay? So the first thing is this again matches like our insight. We don't expect to actually beat the rule-based optimizer because that's actually based on some real insights and all of those things. We are removing all of them. We are removing the human from the loop. So that's where the cost-based optimizer really comes in. So what was happening in CO is the word co-occurrence. So we noticed that actually the rule base is suggesting run combiner and compression because we are dealing with lots of data. Okay? The best performance actually came just having the combiner, no compression, even on these beefy nodes, because combiner and compression together can actually put so much load on the CPUs that compared to our performance, just having combiner alone was 2 times better. We suggested not having combiner and compression. That's why we are actually bad. So what this shows is basically we have to, the models aren't all that well. We are taking a closer look. These results are actually over the summer. My feeling is most of the issues that we are actually having is because our profiling, the tool B-trace that we are using, does add some reasonable amount of overhead. Okay? So I've tried to show that in this graph over here. So this is running the word co-occurrence job, varying the percentage of tasks we are profiling. So 100% means every task we are actually profiling. 1% is just 1% of all the map tasks and reduced tasks are actually being profiled. And you can see that the percent and what is being shown on the y-axis is time without profiling, time with profiling, how much extra that we are actually taking. So all the tasks being profiled, we are actually 30% extra time for collecting the profiles, right? And there are interesting behavior you see, and I'll actually again talk about why and about that offline. So this is not 30% is not insignificant by any means. Although like profiling is 30% is not okay if you are turning on profiling continuously on the cluster. It's probably okay if you are collecting a profile and then optimizing it and to do a run. Okay? At least one nice artifact we saw for word co-occurrence is at least the profile is, even with a small fraction, is able to get us to close to the best performance that we had with the full profile. But there is tons of work to be done. And no, this is actually very specifically for word co-occurrence. The worst we have actually seen is 60% overhead for word count. But yeah.
So you can't conclude globally that about 10% of
Oh, that we have done. Yes. Oh, that we have done. So for everything. This graph is only for word co-occurrence. Yeah. Because the fact is, like 1,000 map tasks that run, 10% will actually give you very good information. The thing is, just 1% actually gives, enables you to find some of the bottlenecks and actually fix them. Okay, doke. Yes, Dan.
On the previous slide, when you showed us the relative speed up, did that include was that for the running time with the profiler turned on?
No, these are all without the profiler, because we collect profiling and then use it and then get the best ready, run it with that, run it multiple times with that, yeah. Okay, so 1 minute to finish. So I'm going to skip a couple of slides on the what if engine. This was what I showed you earlier. This is as estimated by the what if engine based on one profile. So that looks reasonably good, except because of the overhead the profiling is adding, this actually is kind of slightly shifted up. Every function we are profiling, we collect a little bit more time. So there is some issues like that. And I'm going to skip this guy again. It's a what if engine. I'm going to skip this one too, just quickly wrap up with my final part, which I can definitely do in 1 minute. So what are we doing here? Ongoing work and essentially a wish list. So one of the things we are looking at is these. Nobody runs single jobs. They run these big pipelines. This is actually the pipeline for TF-IDF, term frequency, inverse document frequency, which involves at least 3 jobs. So it's much more natural for users to specify them as these, long and sort of thin pipelines. They're often connecting together individual jobs written by other people, right? And there are a lot of opportunities just sticking at the MapReduce level, not even bringing in anything like pig or whatnot, to do 2 types of optimizations. Do vertical packing of jobs. So essentially what we have done is taken these 2 and we're running them as a single job where these functions are not gone, they're still there, they're chained together. And sometimes do horizontal packing if we have a larger workflow. So we call this approach stubby, the idea being, from tall and thin to short and fat. Although this is again just another optimization problem. Sometimes when you make them short and fat, the performance can actually be much worse. That's one of the things we are spending a lot of time, and some of that is made it into the version 0.2 of the Starfish release. Profiling overhead remains very high on the wish list, although I think there's probably some commercial help or commercial tools we might have to bring in to be able to address that. We are working on new features in the elasticizer, and one very nice thing, as I keep mentioning about the cloud, is you have now the ability to run clusters where maybe you're there's some linear algebra operation. So first you're processing a lot of text to generate these matrices, and the matrices are small enough that you probably can put them into one of these high performance computing sort of machines with everything in memory, and even use GPUs to actually come crunch very very efficiently. So there are opportunities like that. Using spot instances. We are working on those data cycle workloads, where to actually do the computation on the data serving system, log aggregation, analytics. That is it. I'm open for questions.
Amazon is notorious in terms of the variance of execution because of the access to the disks, the network access, the job spin up overhead and stuff like that. So how do you compensate for that really high variance when you're doing profiling or feeding your models?
Well, so again, one thing I've sort of observed, and this is, I could be in our experiments, we are not seeing that high of a variance. Most of the numbers I actually showed you are not seeing that much of variance. So it could be that we are using the specific data center from which we are getting our machines or whatnot is actually not seeing that much of variance. So that's one observation, right? But everybody says you have pretty high variance, and what is our story for dealing with high variance? Now the thing to keep in mind is that so when we collect our profiles, right? Most of these profiles are really trying to, so things like data flow that goes through are not affected by variance in the computation itself, right? Cost statistics are. So things will really go bad if what happened for us was when we profiled the map function, that had very high variance, and when we profiled the spill, that doesn't happen. So as long as the relative things stay okay, even if we are running things on when the system was relatively highly loaded, the configurations that we end up recommending are actually, they're sort of specific to the job such that they will still run fine when the system is lightly loaded. Although that's something which, so the point is, when we are working on Amazon EC2, and because we didn't see much variance, we couldn't really test it out, but over the summer we are working with Yahoo. So there we want to do it, we were trying to, this guy here, the robust and adaptive tuning. Specifically, what we are focusing there is, suppose I collected the profile when a lot of users were using the system. Are the recommendations that we come up with good enough for when the system is lightly loaded and as well as heavily loaded? That we're trying to answer there. And I don't have a very crisp answer for you right now. I know about that, but somehow my impression was that's only for the PIs who have a grant off of that.
Well,
Is that?
that is, and you might be able to sneak in, or on piggybacking on other PIs that might have a proposal.
Okay. Yeah.
I don't think it's very heavily used. I'll say it that way.
Yeah. Thanks for letting me know that.
So
Yeah.
you showed us that the rules-based optimization actually does pretty well. So I was wondering, have you thought about a mixed approach in which you combine the rules with your model-based optimizations?
So the question was rule-based optimization, at least for the high-end clusters and lots of data, for those workloads that we ran, was doing pretty well, right? So the question was, what about a mixed approach that combines the rule-based and the cost-based? In reality, that's being one example, right? How to leverage that information. So in reality, our cost-based optimizer is also actually leveraging some information from the rule-based because, first of all, we are dealing with these 14 parameters. And how do you decide which parameters for a particular job to actually focus on? There is some insight that could come in here, right? Now, the way in which you can use our optimizer is basically there's a nice GUI. You can actually go in there and pretty much suggest the range of settings or the parameters you want us to sort of focus on, and that way, we can suggest settings for that. Even the insight that we brought in on which parameters affect maps, which parameters affect reduces, we're sort of bringing in domain knowledge. So my answer, or what I was sort of dealing towards, is rule-based optimizer is really based on somebody's domain knowledge being encoded and that being used along with the searching or whatnot. That is, I think, definitely the best approach, and we are sort of slowly going along that route. But the problem with the rule-based specifically is their guidelines. They don't tell you, look, set your parameter this much. They can actually tell you, if you're seeing a lot of spills, then look at these parameters and try to optimize them, right? Then cost-based can actually take over for which parameters. Right?
Do failures in the cluster affect kind of any of the planned choices, or do you consider them at all? Do you need to consider them?
As we are moving towards, actually, I didn't show some set of results on, even scaling the number of compute units by one more order of magnitude, 50 nodes and 100 nodes. So there, we are actually seeing a lot of I've been in the last couple of days, I've been debugging a problem where what happens is suddenly DNS will fail on EC2, and that is actually happening when profiling is going on, and that causes some issues in the profiles and things being missing and incomplete. So there are definitely issues that come up with failures. But your specific question was, if I know that this is probably a cluster where there are bigger chances of failure or things like that, do you set parameters differently? I would think yes, because sometimes what happens is if you think a lot of failures can happen, you might want to have more map waves and reduce waves. Because what will happen if you just had one wave, something fails, and then that has to be rerun again. So the overall completion time can be very large. So these are all things that we could bring in our optimizer. As I said, there was this metric we are trying to optimize for. It could be one metric, it could be a combination. So we could potentially write different optimizers that make different choices to give a suggestion. Yeah.
I have a question about the rule-based again. So you said they're guidelines, right? So in your evaluation, how did you actually implement them? If it said you should generally set this parameter to be higher, what did you set it to?
Tough question. We picked, I think what we ended up doing was, back. So I think showing a slide will help answer that question. Okay, so many of these parameters actually have to deal with memory. So what we end up doing is finally, you can't increase it. It says increase memory. You can't increase it beyond, the Java heap size. So what we try to do is try to increase it in such that, subject to these limitations, is the best. Things like that. Although you're dealing with multiple parameters, it's a little bit trickier. There could be other interpretations of the rule-based. My point was just to show that, there are rule-based things that people use for different clusters. Things might not work. That was the main point I was really trying to drive home. As long as we do good with respect to the rule-based needs a human being to interpret it. And you can't afford that in these big clusters and lots of jobs being run. That's the point I want to make.
Can you
there are two questions. One question was like choosing the partition, like one big problem that everybody has in these environments is data skew. So if you don't choose a good partitioning function, and often MapReduce uses hash, which works well a lot of the time, but if there is skew, it can really really break down, especially very significant skew. And the second question was, some of these MapReduce jobs, especially things like if in machine learning, you might be doing some sort of a parameter sweep that the system actually reads in some parameter, and its behavior could very much depend on the user-specified parameter. So I'll answer the second question because that's easier. We don't do anything. So that's a very hard challenge. Just like in database systems, user-supplied parameters are hard to deal with. We don't have an answer right now for that problem. I'll take the first one, choosing the partition function. Partition function is a parameter that we are dealing with. Okay? So as we collect the sample, we also choose the best partition function, especially as we move towards workflows. We are trying to do something even better. This logic of when you can vertically pack things depends a lot on the partitioning function. So instead of sometimes I can choose a partitioning function that, for example, this job, if you see here, this job is basically, it needs the data sort of grouped on D and D. So this is the partitioning key. And the reduce is actually, and these are two attributes. Just think of it as doc ID, word ID. Okay? So the reduce function R2 needs the data partitioned on doc ID and word ID, and for every combination you run the reduce function, right? So here it so happens that this reduce function needs it just partition on doc ID. But here if I choose a partitioning that was on D, okay, as needed by R1, but also internally sorted those partitions on D, W, so that I'm bringing together the D and W combinations also, then I can sort of stream the data through R1 and also stream those individual things over R2 and still preserve the semantics as needed by these reduce functions. So there is more to choosing partitioning functions. Also things like if I, sometimes I can replace the hash partitioning with a sort-based partitioning, and that way get the data sort of nicely partitioned on time ranges or something. So for a future job, I can only access the partition that I needed, because there might be a selection condition that sort of prunes things by time. So that's something we are heavily focusing on in these tall and thin pipelines, this work. Thank you.